Hello, welcome. Today we will look at the embryology of the endocrine system. We'll look at the embryological origin of the different endocrine glands. So we have basically these three different germ lines. The glands that are derived from the diverticuli of the digestive tube are derived from the endoderm. These glands, the thyroid gland, parathyroid gland, and endocrine pancreas are derived from the diverticuli of the digestive tube. So they are derived from the endoderm germ layer. The second germ layer, mesoderm, gives rise to glands that secrete steroid hormones. So we already know that steroid hormones are secreted by different glands, including the sex glands, these gonads, the ovary and test, and adrenal cortex, which secretes different mineral corticosteroids and glucocorticoids and also androgens. The third germ layer is the ectoderm. The third layer is the ectoderm. Glands that secrete peptide and those hormones that are derived from amino acids are derived from ectoderm, like the adrenal medulla, which secretes catecholamines derived from the different amino acids. The main amino acid here is tyrosine, so the epinephrine or epinephrine are secreted by this adrenal medulla, and the adrenal medulla cells are derived from the neural crest cells. You remember the adrenal medulla is composed of these chromaffin cells which act as the postganglionic postsynaptic ganglionic neurons. So they are derivatives of neural crest cells. The anterior pituitary derived from the oral cavity ectoderm. The posterior pituitary has neuroectodermal origin, but the hormones are not produced here. They are stored in the site of production for these posterior pituitary hormones is the hypothalamus, as I hope you would already know. So now we see the development of each of the glands of our body one by one. To begin with, we will talk about the pituitary gland. So here I want you to note these pointers. So whenever we talk about the development of an organ, you have to know the chronological age of this development. This is the approximate time of the intrauterine life where the organ, or in this case the gland, develops. The germ layer is also an important aspect for the embryology of an organ development. So for the pituitary gland, the chronological age is in the middle of third week of intrauterine life. And for the germ layer, it arises from two sources, because we already know that the pituitary gland is divided into two, the adenohypophysis and the neurohypophysis. The adenohypophysis, or the anterior pituitary gland, is derived from the surface ectoderm, and the neurohypophysis is derived from the neuroectoderm. So now we will talk specifically about the development of the anterior pituitary gland, or adenohypophysis. This gland is developed from the surface ectoderm, as we already said. So we have the primitive oral cavity or stomatium, and from the ectodermal lining of the roof of this oral cavity, future mouse seen cranially in relation to sphenoid bone. So it has two sources, the stomedium and the buccopharyngeal membrane. So during the process, the ectodermal lining of the roof of the primitive oral cavity invaginates to form a pouch. This pouch is called Raticus pouch. Will you see this on page? So here, this is the invagination of this ectoderm, this ectodermal lining of the roof invaginates to form this Raticus pouch. And this pouch develops in, as we already said, in the third week of the intrauterine life. Later on, this pouch will be cut off or it will degenerate from the primitive mouse or the stomedium. So, as this is cut off from the primitive mouse, then there will be the formation of the gland. So, this diagrammatic representation shows us the development of anterior pituitary gland from the ectodermal lining of primitive oral cavity. Here we see that this Raticus pouch is formed by the invagination of this ectoderm, and here it grows and forming the anterior lobe of the pituitary gland. And this is a general diagram showing the double origin of the pituitary gland. This neuroectoderm for the posterior pituitary gland, and this one the Raticus pouch or the oropharynx ectoderm for the formation of anterior pituitary gland. We see here this pouch is cut off here, and within this fossa of the sphenoid bone, it will form the posterior and the anterior lobe of the pituitary gland. Another diagram here shows the formation of the posterior pituitary gland here from the floor of hypothalamus here. As it invaginates, it forms this posterior pituitary gland, and the ectodermal lining of the premoral cavity as it forms Raticus pouch. Finally, after it is cut off from the stomedium, it becomes adenohypophysis. We will talk about the details and the videos later on. So the Raticus pouch has different walls. Here it has anterior wall and posterior wall. The anterior wall of the pouch proliferates extensively to form the pars anterior. So here we see this part of the gland, the pars anterior or the pars distalis part proliferates. It forms this pars anterior. The posterior wall of the pouch remains thin. Here you see pars intermedia, which is thin, and here is an intraglandular cleft. So this cleft is within the gland, as we can see from the name, intraglandular. So this persistes as hypophyseal cleft within the gland. Here we see the small extension of pars anterior that grows upward cranially to form this part of the gland, the pars tuberalis, all making up the anterior pituitary or adenohypophysis. The pituitary gland, the posterior pituitary gland or neurohypophysis, develops from an invagination of neuroectoderm of hypothalamus or floor of third ventricle of the brain and sphenoid bone. This neuroectodermal diverticulum from the floor of the third ventricle and ectodermal pouch from the roof of stomedium fuse with each other to form hypophysis cerebra called posterior pituitary gland. So as this neuroectoderm of the hypothalamus or the floor of this third ventricle invaginates, and a sphenoid bone, and when it fuses with each other, they form neurohypophysis or the posterior pituitary. Now we see the possible congenital anomalies of these glands. We have first one is ectopic posterior pituitary, pharyngeal hyposis, agenesis or hypogenesis of the pituitary gland, the duplication of pituitary gland, there can be congenital tumor of the gland. So now we will see each of them one by one. The ectopic posterior pituitary is, as we see, it's ectopic, so it's absent in its normal position, absent normal posterior pituitary gland. Within the cella turcica of the sphenoid bone, bright spot, and with the ectopic bright C gland at another site, such as the median eminence. So it's located ectopically. The development is because of the incomplete caudal extension of the encephalon during embryogenesis, and the effect will be pituitary dwarfism or lack of growth hormone. First, the second one is pharyngeal hyposis. As we see, it is the hyposis or the pituitary gland found in the roof of the oropharynx. So it's a remnant of the stalk of the hypophyseal diverticulum and the roof of the oropharynx. An ectopic pituitary tissue is found attached to the roof of the mouth, and is caused by the failure of radicular pouch to separate from the roof of the mouth. As we said earlier, this radicular pouch degenerates or is cut off from the roof of the mouth, the normal development of the gland, but if it fails to separate, there will be pharyngeal hypothesis. This is an anomaly. So here we see this radicular pouch by its failure to separate. Here is found in the roof of the oropharynx. This. The third anomaly is the agenesis. So or hypogenesis of the pituitary gland. This is absence of the gland. So if the gland is absent, it's incompatible with life, so the infant will die. It also leads to panhypopituitarism. This is a condition of inadequate or absent production of the anterior pituitary hormones. So we see here this stomidium didn't invaginate, so it couldn't form the pituitary gland, the anterior pituitary gland. This diencephalon didn't form the posterior pituitary gland. The fourth anomaly is the congenital tumor of the gland called craniopharyngioma. This tumor arises from a remnant of radicular pouch. So we will see the effect of this tumor. The first one is it increases the intracranial pressure. There will be hydrocephalus, disrupts the function of the pituitary gland, and also it could damage the optic nerves. If they damage the optic nerve, so there will be visual field disturbances. Then we have these benign tumors of the CNS, the epithelial tumors that typically arise in the hypothalamus or the optic chiasm or the third ventricle. So we are done with the development of the pituitary gland. We have seen the germ layer from which the gland develops. We have seen the chronological age of the gland's development, and finally we have seen the common developmental anomalies of the gland. Then we will talk about the development of the thyroid gland. The thyroid gland, as you already know, is the largest endocrine gland of the body. So its location is here. The lower part of the front and the side of neck opposite to this C5 up to thoracic one vertebra, and it's an H-shaped organ that consists of vertically lying right and left lateral lobes that are connected by isthmus centrally. They are connected by an isthmus. And the chronological age of this gland development is at the third week of intrauterine life. This gland is the first endocrine organ to develop, and its germ layer is the endodermal diverticulum or the thyroglossal duct. So remember, this thyroglossal duct or the endodermal diverticulum is the germ layer for the development of thyroid gland. The site of its development is in the floor of the pharynx below and behind the tuberculum impar of the developing tongue. The source of this gland is the median thyroid diverticulum. Thyroid gland, as I hope you have already seen, is composed of two different types of cells: the follicular cells that have endodermal origin and the parafollicular cells, or these clear cells that secrete calcitonin, are derived from the ultimobranchial body from caudal pharyngeal complex. We will talk about this ultimobranchial body later. So during the development of this gland, during the development of this gland, so there will be two lingual swellings between the first and second pharyngeal arcos, or the tuberculum impar. Behind this tuberculum impar, on the dorsum of tongue, there will be a small foramen that's called foramen cecum. Foramen cecum endodermally thickened and it grows downward, and this downward growth forms the thyroglossal duct, which we already said is the origin of the thyroid gland. Distally, this thyroglossal duct forms bilobed masses. These two masses are the right and left lobes of the thyroid gland, and the downward growth of the foramen cecum is induced by the caudal pharyngeal complex. This complex is formed by the fourth and fifth pharyngeal pouch, and their one function is the lateral thyroid element. So this lateral thyroid element is eject tissue for the downward growth, and it projects on either side of the thyroglossal duct. It fuses with the thyroglossal duct, so it forms the final shape of the thyroid gland, the butterfly or H-shaped thyroid gland that's connected centrally by isthmus. Finally, the cranial most end of the duct will degenerate, and the remnant foramen cecum is normal. So here we see this hypopharyngeal eminence component from the pharyngeal arcs 3 and 4, and there will be the formation of this thyroglossal duct by the downward growth of this foramen cecum, and this diagram shows us the migratory paths taken by the thyroid gland as it descends from the region of its formation here to its location in the neck anterior to the trachea. So it follows this path enter to the hyoid bone to this thyroid cartilage, and finally it takes this position here. So during the development of the thyroid gland during the fourth week, this is the thyroid diverticulum growing downward, and as it grows downward, these ducts will be formed, and finally we have this thyroid gland during the fifth week. Another diagram here showing the sequential development of this thyroid gland. So we first start the endodermal thickening. So this endoderm will be thickened, then it will be depressed. This endodermal thickening will undergo depression, and there will be the formation of thyroglossal duct, these ducts. Then the lower end of this thyroglossal duct will bifurcate, so this is the bifurcal lower end, and then these two masses will develop into the two lobes of the gland, and finally we have this lobe, this right and left lobes connected by this isthmus of the thyroid gland. This is the remnant of thyroglossal ducts, which is the foramen cecum. Now we see the anomalies of the thyroid gland. The first one is the lingual thyroid, as we can see from the name. It's a lingual, it's located at foramen cecum. So it persists where it's developed at the foramen cecum. The retroesternal, so you can see from the name, it is posterior to the sternum. So the thyroid gland develops behind the thyroid. The thyroglossal cyst is when the duct persists throughout its course and it forms in cystic swelling. The lobus pyramidals means the lobes of pyramids that formed when the caudal end of the thyroglossal duct at the middle of the isthmus persists. They form these lobes of pyramids called lobus pyramidals. Ectopic thyroid gland also can be here, and intralingual thyroid is the formation or the development of the thyroid gland at the muscles of the tongue. It is intralingual, so it's the muscles of the tongue. Suprahyoid is if the thyroid gland develops above hyoid bone, and the thyroglossal fistula. Here we see that it's fistula, so there is a communication between the thyroglossal cysts exteriorly with the thyroglossal duct. So both the duct and the cyst communicated by a fistula, the thyroglossal fistula. This diagram shows us the different anomalies. So normally the position of thyroid gland is here in the neck, anterior to the trachea, but it can be found here. So it's found here at this foramen cecum. We call it lingual thyroid. It can be intralingual if it is found at the muscles of the tongue. It can be suprahyoid here. It is superior to this hyoid bone, and it can be infrahyoid if it is found below the hyoid bone. So another diagram here showing us the development of the thyroid gland. We have this foramen cecum. This is the site of origin of thyroglossal duct between the floor of bronchial arches 1 and 2. It's here that the thyroglossal duct forms. This thyroglossal duct rise to the endodermal downgrowth of the thyroid epithelium. From it, developing tissue invades this hypobronchial mesenchyme, which gives capsule and septa. And the site of these are the sides of the thyroglossal duct as it moves up with the protrusion of the tongue, and we have this retroesternal thyroid. So if the developing process, that is the downward migration of the thyroid gland goes too far, it will be retroesternal, posterior to the sternum. So now we are done with the thyroid gland development. Then we will talk about the development of parathyroid gland. So the embryological origin of these parathyroid glands are the endoderm of the third and fourth pharyngeal pouch. The third pharyngeal pouch specifically gives rise to the inferior parathyroid glands. As we know, the parathyroid gland are four parotid glands. Two of them are superior and two of them are inferior. So it's the third pharyngeal pouch that gives rise to the inferior parathyroid, while the superior parathyroid glands arise from the fourth pharyngeal pouch. And due to their relatively long course of descent, the inferior ones to be located inferiorly, the course of their descent is relatively long. So the final location of the inferior glands is more variable. So when we talk about the third pharyngeal pouch that forms these inferior parathyroid glands, they divide into the dorsal and ventral rings, and the dorsal ring gives rise to the inferior parathyroid gland, while the ventral wing of the pouch leads to the formation of the thymus. Later on, the thymus will lose its connection with the pharyngeal wall and it descends inferomedially to fuse with the contralateral portion in the anterior mediastinum. It's about the development of thymus from this ventral wing of the third pharyngeal pouch, but our focus here is the formation of the inferior parathyroid gland from the dorsal wing. So in the seventh week of gestation, the inferior parathyroid gland is separated from the posterior pharyngeal wall and they follow the path of the thymus to reach their final destination on the posterior thyroid. So this is the normal location of the glands on the posterior surface of the thyroid gland. The fourth pharyngeal pouch, which divides again into dorsal and ventral wings. The dorsal wing differentiates into the superior parathyroid glands, while the ventral one differentiates into the ultimobranchial body. This body fuses with the posterolateral thyroid and gives rise to the parafollicular or C or clear cells of the thyroid that secrete calcitonin. In the seventh week of development, the parathyroid gland is separate from the pharyngeal wall and they attach to the posterior surface of the thyroid, as we said for this inferior parathyroid glands. And here, due to the comparatively longer course, the final location of the inferior parathyroid is more variable, and ectopic parathyroid tissue can be found anywhere along their pathway of descent. So here we see this third and fourth pharyngeal pouch, which form this. The third pouch forms this dorsal and ventral wing. The dorsal wing will form the inferior parathyroid glands, and this ventral wing, as we said, will lead to the formation of the thymus. For the fourth pharyngeal pouch, it also has this dorsal wing and this ventral wing. The dorsal wing will give rise to the superior parathyroid gland, and this ventral wing will form the ultimobranchial body. Now see the congenital anomalies of the parathyroid gland. The first one is hyperparathyroidism. So as we can see from the name, it's hyperparathyroidism. So the parathyroid gland starts creating high amounts of parathyroid hormone, and when there is high amount of parathyroid hormone in the bloodstream, there will be an effect on the calcium levels of the blood. They will rise, and this will lead to the damage of bone and organs. Another condition, hypoparathyroidism, when one or more of the parathyroid glands are not active enough. So when there is no enough parathyroid hormone in the blood, this will lower the level of calcium in the blood, and there will be high phosphorus. Then we see about the development of the suprarenal gland. The suprarenal gland, also called renal gland, contains outer cortex and inner medulla, as we already know. And so these different layers of the gland, the cortex and the medulla, derive from two different origins, the mesodermal and neuroectodermal. The cortex is derived from the mesoderm, and the medulla is from the neuroectoderm, that are from the neural crest. So talk about the sources of the gland. The cortex develops from the coilomic epithelium in mesodermal origin, and we have fetal cortex and definitive cortex. The fetal cortex is composed of larger acidophilic cells, these are eosinophilic cells, and the definitive cortex is composed of the smaller basophilic cells. The medulla, as we already said, is from the neural crest cells. These neural crest cells act like the postganglionic sympathetic neurons. And at the end of the second month of intrauterine life, the section of fetal body is located at T6 up to T12, in which the suprarenal ridge is located. So this is the initial process in the development of this suprarenal gland. There will be suprarenal ridge in this region, and the region between root of dorsal mesentery suspending the primitive gut and the developing gonads. There is the coilomic epithelium that forms developing ridge, and this ridge is called suprarenal ridge, as we already said, located at the level of thoracic 6 up to thoracic 12 vertebra. And the suprarenal ridge is formed by the proliferation of the mesothelial cells. It's lined by the coilomic epithelium and again mesodermal in origin. So now we will talk about the development of the renal cortex. As we said, it develops from the mesoderm, and on both sides of the suprarenal ridge, just superior to developing gonads, there is mesonephric artery. So we'll come to this later. There is a mesonephric artery, and above the suprarenal ridge, the clusters of mesodermal cells will proliferate. And this suprarenal ridge will be disturbed by the formation of two structures. One is the neural crest cells, and second, venous sinuses. The mesonephric arteries start to invade the suprarenal ridges, then they reach the venous sinuses in radial fashion, and they form mesonephric capillaries. You see, when these arteries reach the venous sinus in radial fashion, there's clearly formation of capillaries, and the mesothelial cells are sandwiched between the mesonephric capillaries. And the cells, the arteries, and the ridges here are lined by the venous capsule, and when the cells reach at the venous capsule, the venous sinuses, they become eosinophilic. The inner one are eosinophilic, and the outer one become basophilic. These persist at the periphery, and they become basophilic. And at birth, the inner eosinophilic cytoplasmic filling cells, so these inner layer of cells develop into the fetal cortex, and the basophilic cytoplasmic filling cells become the definitive cortex or the outer cortex. And finally, this will develop into the dona glomerulosa, which is the outermost layer of the renal cortex. After 2 weeks of birth, the fetal cortex, which is the inner layer of the cortex, will degenerate, but the definitive cortex will persist. And as it persists, that form the remaining layers of the parenal cortex, the zona fasciculata and the zona reticularis. Finally, the three layers of renal cortex, the glomerulosa, the zona fasciculata, and zona reticularis are formed. So here we see this suprarenal ridge formed by these mesodermal cells from the coilomic epithelium, forming this definitive cortex and fetal cortex. This diagram shows us the relative percentage of the renal cortex and the medulla during the development of the gland. Initially, during the 5th months of the intrauterine life, most of the gland is by the fetal cortex. 75% is the fetal cortex. The medulla here is very small, making up the 5%, and the adult cortex is. During the birth, there will be the adult cortex will make 35%, the fetal cortex here 50%, and the medulla makes 50%. Finally, the cortex will be 80% and the medulla will be 20%, and the fetal cortex is degenerated.